Hey everyone, welcome to this explainer. As a senior engineer, I'm going to walk you through a classic startup architectural teardown today, and we'll be using the story of ScaleCorp to do it. You know, every great tech company starts the exact same way, with a big idea, a small budget, and absolutely no idea what's coming. Let's dig into the fundamentals.
So here is the architectural journey we'll unpack today. We'll look at the startup baseline, the dangers of a single point of failure, the vertical scaling trap, designing horizontal systems, and finally, the tricky problem of state management. All right, let's jump right in.
Section 1. The Startup Architecture, or the MVP baseline.
We begin at the very start of the company's life cycle. Every startup starts with an MVP, right? And here we see our founders, Rabbit and Turtle, launching ScaleCorp with just one product and a single server. Rabbit was fast, impatient, and always 3 steps ahead, while Turtle was calm, careful, and honestly, almost always right. Now, in the beginning, life was incredibly simple. That one server sat quietly in the corner, handling every single customer request that came through the door. The queue was short, responses were fast, and Rabbit and Turtle felt like absolute geniuses. In engineering, this is what we call a single-node architecture. And hey, it works perfectly when your traffic is low and predictable. By definition, it's a system design where one machine handles all incoming customer requests and back-end jobs. One machine, one job, literally 0 problems. This is how almost all systems start. But, as we're about to see, they rarely stay that way.
Moving on to Section 2. Single point of failure and the viral incident. Because, let's face it, systems don't stay quiet forever, especially not during what ScaleCorp experienced as Viral Tuesday. Take a look at this graph spike. Traffic shot straight up, absolutely flooding their single machine with thousands of concurrent requests. Hundreds of customers quickly turned into thousands, stretching out as far as the eye could see. ScaleCorp had gone completely viral. Rabbit's eyes lit up with excitement, but Turtle, well, Turtle knew exactly what this meant for their hardware.
That poor server just wasn't built for this. It gave up. Requests slowed to an absolute crawl, and eventually the system dropped completely offline. Customers waiting at the back of the queue just threw their hands up and left. It's a nightmare scenario. Every single second that server was down, ScaleCorp was burning through their hard-earned customer trust. One machine doing the work of 100 was just never, ever gonna survive.
In the industry, we refer to this devastating bottleneck as a single point of failure. The quote here hits the nail on the head. One machine holds everything together, and when it breaks, everything breaks with it. It is the most critical vulnerability a young architecture can have. Think about it. Your entire business is riding on the health of a single motherboard. That's a massive risk that no growing company can afford.
Which brings us to Section 3, the vertical scaling trap or brute force solutions.
Now, when disaster strikes, I've seen 100 startups make the exact mistake Rabbit proposes next, trying to brute force the patch by buying a bigger, faster server. This is known in engineering as vertical scaling. The idea is to rely on a massively muscular, supercharged server. You know, more memory, more processing power, just more of everything. The logic is definitely tempting. Just make the one machine stronger and the problem goes away, right? Well, Turtle was not impressed. So, here is the crucial point. Vertical scaling eventually hits 2 invisible walls: physical hardware limits and exponentially rising financial costs. Think of it kind of like having one clerk at one desk. When things get busy, you give that clerk a faster computer, then a bigger desk, then, I don't know, 5 energy drinks. And sure, it works for a little while, but physically, there is only so big a single machine can get. And financially, every single upgrade costs significantly more than the last. And as you can see, Rabbit hit that financial wall almost immediately. The server was already running at its absolute maximum, and the next physical upgrade was going to cost more than the company made in a whole month. And worse, they still hadn't resolved the underlying single point of failure risk. Turtle asked the golden engineering question here. What happens to every single customer if this one machine goes down for even 10 minutes? Rabbit had absolutely no answer.
So we hit Section 4, designing horizontal systems, the smart pivot. This financial roadblock forces a complete architectural rethink led by Turtle. Let's compare the 2 philosophies here. Instead of one massive machine, Turtle proposes a highly scalable design using 3 standard servers working together side by side. Each one just handles its share of the workload. But this introduces an entirely new mechanical question. When a customer walks in, which server do they actually go to?
To make this work, we have to introduce a load balancer. Acting as the traffic cop right at the front door, you need a system greeting every incoming customer and pointing them to whichever server is currently free. Now, the load balancer doesn't do the actual computational work itself. It just acts as a perfectly fair dispatcher.
The load balancer executes 3 precise steps to ensure fair distribution, so no single node ever drowns in traffic. First, it receives the incoming user request. Second, it looks at all the backend servers and identifies the one with the most available capacity. And third, it seamlessly routes the request to that free server. It's brilliant.
Growing wide rather than growing up gives us 3 massive technical benefits: infinite scaling, high fault tolerance, and seamless user routing. Literally, there is no ceiling anymore. When traffic grows, you just add another server to the row. And there's no single point of failure. If one server breaks, the load balancer quietly stops sending traffic to it and just routes everyone to the healthy machines. The shop stays open, and the customers never notice a thing.
All right, final part. Section 5, the state management problem, or the next bottleneck. ScaleCorp is saved. The physical servers are running flawlessly, sharing the load and preventing crashes. Turtle successfully deployed the new server racks into production, and ScaleCorp celebrated. 3 servers, a robust load balancer, no more outages. But any senior engineer knows that fixing one bottleneck simply uncovers the exact next one down the line.
Here's the new headache. Where did the user's shopping cart go? Think about it. If a user adds an item to their cart on server 1, and the load balancer sends their very next click over to server 2 has absolutely no memory of them. A user walks up and says, "Hey, where's the item I just added?" Server 2 has never seen this customer before in its life. It doesn't have the cart. You see, the servers split the traffic perfectly, but they also split the application's memory. This brings us to the wonderfully complex world of shared state and databases, represented by this glowing central repository. The load balancer is working great, but now these 3 independent servers need a way to agree on a single version of reality. So I'm going to leave you with this provocative thought to ponder before our next explainer. How do multiple machines agree on a single version of reality? If you are building systems out there, the problems Rabbit and Turtle are facing right now are the exact same problems every engineer faces the moment their work starts to scale. We've solved the hardware bottleneck for sure, but the messiness of keeping everyone on the exact same page, that has just begun. Keep this architecture in the back of your mind, and I'll see you in the next explainer.